Okay, I think previously I have taught you about equation of continuity and Bernoulli's principle, hydrostatics, Pascal's law, and all that. Okay, I will do some numericals on that, but we had not done surface tension. Okay, so uh, we'll just understand the concept of surface tension. Okay, so let us say this is a container. Okay, so what happens, like let us say this is the surface. Okay, so let us say this is my surface. So the molecules of the liquid inside, okay. So let there be a molecule inside. So it will be surrounded by many other molecules. It will be surrounded by many other molecules, okay. So this molecule will get attracted by the molecules surrounding it, right? These molecules will be attracted by molecules surrounding it or whatever. Like you can draw a circle and can, so you will have this molecule is being attracted by molecules. It is surrounded by certain molecules, so it is getting attracted. Okay. But when you go to the surface, let us take a molecule which is at the surface of the liquid. So here you will have a semicircle, okay? It will be a semicircle or hemisphere or whatever. So you will have some molecules which are below. Okay. So what happens? There is a net force acting on the molecule at the surface. Okay, because there is a net force, all the molecules on the surface are getting pulled from molecules which are inside. Okay, when your surface is getting pulled, that means there is a net force on it. So suppose you are trying to suppose uh, I am pulling something. Okay, it is trying to go out, but I am pulling it. When that is being done, like that is called, it is under tension, right? So tension is nothing but a force. So the surface liquid being in a state of tension is called the phenomena of surface tension, right?
Yeah.
So there are many phenomena which are linked with surface tension, like capillary rise and all. So, in the trees or big trees, the way the water is supplied, water is going from the root to the leaves or whatever. That that water is going up because of the capillary rise. Okay, so that is a phenomena of surface tension that I will explain. Like when surface tension is low, it will try to spread over a bigger area. Okay, when surface tension is low, it will try to spread over a bigger area. Okay, so and also surface tension is a property of the liquid.
Yeah.
Okay,
Correct.
so the formula we will not get into the derivation. So we'll just do like surface tension is equal to force per unit area. A force per unit length. So the unit of surface tension is Newton per meter. Okay. So yeah. Um, and also the surface tension or otherwise can be written as energy per unit area. Okay. So which is nothing but your joule per meter square. Okay. So either you can say surface tension as force per unit length, or you can say surface tension is energy per unit area. Uh, a surface tension is a property which varies with temperature. at higher temperature the surface tension decreases. Okay, so and for example, this soap solution, okay, it will have less surface tension as compared to the water. That's why when you are using soap solution for cleaning, so what happens? The dirt remains inside your clothing. Okay, so the soap solution need to enter into it. Okay, so because it has lesser surface tension as compared to water, then it will penetrate into it. Okay, so also you might have seen the hot water also will clean better, because when you are heating the water, the surface tension decreases. So it will have better tendency to enter inside. Also, we say that hot foods or hot soups are much tastier as compared to cold soups. Why? Because if the surface tension decreases, the it spreads over a bigger area. Okay, so if you a hot food or hot soup, if you are when you are tasting it, it will cover more area of your tongue. That's why you will feel it quite tasty. You will find it tasty as compared to colder food or colder this thing. So there are many phenomena in uh, the physical world which you can relate to surface tension. Okay, so um, okay, so this capillary region is so then there is something called this. We'll just touch the formulas rather than going into too much of derivation. Okay, so when a bubble is formed, let us say the water bubble is formed. So let us say this is my bubble. Okay, let us say this is a spherical bubble. Okay, so when a spherical bubble is formed, there is some pressure acting inside and some pressure acting outside, right? There is some pressure acting inside and there is some pressure acting outside. Okay, some pressure acting outside. So let us say this is Pi and let us say this is Po, right? So yeah, always the pressure inside the pressure on the concave surface or pressure inside the bubble will be higher. Okay, if it is not higher, the bubble will not form, it will collapse because outside some force is acting.
Yes.
So it will collapse. So because there is a bubble is getting formed, that means inside pressure is high. Okay, so by how much it is high, we can derive using surface tension here. So you just take a cross section here. You just take a cross section. So if you take a cross section of a sphere, okay, this is a sphere. Okay, right. So let us say this is my sphere, and if you have cut it from the middle. Okay.
Yeah.
So now this sphere has a radius of r, right? Let us say this sphere or a bubble has a radius of r. So this bubble has a radius of r, whereas this perimeter, right? This perimeter is 2 pi r. This perimeter. So on this perimeter, actually, your surface tension is acting. A surface tension acts on a line. Okay.
Yeah.
On this perimeter, surface tension is acting. This is surface tension is acting on this perimeter, right? So throughout the perimeter, the surface tension is acting, and on this area, like on this area, okay, this hatched area, okay, on this area, your Pi is acting because it is the pressure acting inside. Okay, so what is the force exerted by Pi? That force is equal to Pi into pi r square, right?
Yeah.
and this has to balance the force due to surface tension. Okay. So the force due to surface tension is equal to uh, surface tension. Let us say this is called as S, sir. Okay, S into 2 pi r. Okay. So normally in your exam there will be a question, what is the excess pressure inside a bubble? Okay. So here this pi, this is, you otherwise you can call it as pi minus pu. That means
Change in pressure.
change in pressure. Outside there is atmospheric pressure acting. Inside there is higher pressure acting. So this pi minus pu
Delta
is
P.
otherwise can be called as delta p. Okay. So delta p into pi r square is equal to surface S into 2 pi r. Okay. 2 pi r. Okay. So that means your delta p is equal to S, pi cancels, S, and this is 2s by r, right? 2s by r. Right. So this is for a liquid water bubble. Okay. For a soap bubble there will be two surfaces. So for a soap bubble
4s.
delta p is equal to 4s by r. Okay. So for a soap bubble delta p is equal to 4s by r. And there are some other things like, let us say you have water, you have soap solution, you have mercury. Okay. This mercury
Does not take
mercury surface tension will be much higher
It does
compared
not
to
take.
that of water. That's why mercury does not weight the surface.
Yeah.
Okay. Soap solution surface tension will be lesser than soap and lesser than water. That's why it will weight more and it will enter into the it will weight the surface more. So it will enter inside your clothes and it will clean things better. Okay, so there are, I am not able to remember exactly what is the value, but what I feel is, yeah, something like
Water is
0.04 Newton meter or whatever. There are different values for this.
Water is 0.075.
0.075, okay.
Solution soap is 0.08, around that much.
No,
Oh,
so
no,
it should be less.
No. Soap is not that. Mercury is that much.
Mercury how much?
Around 0.04. Water is
Okay,
that much.
0.04. So mercury is much higher than the water, right? So that's how, like these surface tension value, it is a property of the liquid, and for solving any numerical you will be given the value of surface tension. So always remember that surface tension is nothing but force per unit length. Okay. So how he has derived this formula for surface tension, And how you get this S is equal to F by L? He has given, yeah, so the creation of more surface, keeping other things like volume fixed requires additional energy. Okay, so let us say you have already have a surface, water surface. Okay, so you have a surface, so you want to increase this surface area. Okay, so without adding energy, you cannot increase the area of any surface, because when you are trying to pull it, these molecules inside will try to pull it back. Suppose I have this much of area. I want to increase the area by this much. So this side will try exerting that force. So easily you cannot do it. Okay. So let us say this is a film or this is surface, and let us say this is my length L. Okay, this is my length L. So let a force F acts on it. We are applying a force, and it moves by a distance d, right?
Okay.
So it moves by a distance d. Okay. So the work done will be F into d, right? We are applying a force on a d. But how much change in surface area is there? So this change in surface area is d into L. Okay. So your change in surface area delta A is equal to this much d into L. Okay. So surface energy. So when this is the surface area. Okay. So your surface tension, actually surface tension is equal to energy per unit area. Okay. So in this case your okay. So your energy is equal to surface tension into area, right? Extra area delta A. Okay. So this is your energy. Okay. So delta A, which is nothing but S into 2dl, right? This is your energy. So whatever work you have done, that will get stored here, that will get stored in the surface as energy. If you are pulling something, then it will be in equilibrium, but it will stored in the surface as energy. Okay, that's why work done is equal to energy stored. Okay, so your work done is equal to energy stored. Okay, so what is your work done? Your work done is equal to F into D into L, right? Yeah. And your energy stored, you have got surface tension. This is, remember, surface tension is equal to energy per unit area. Okay. So this is equal to, we have find out that energy stored is equal to S into 2 into D into L, right? So your dl cancel. Okay. S into 2dl is equal to F into D. Sorry. So work done is equal to force into distance, not L. Sorry. Okay. Work done is equal to force into distance. L will not come there. Yeah. Okay. So if dd cancels, then S will become F by 2L, right? Here. So here in this case, work done is equal to F by surface tension is equal to F by 2L. Okay. The quantity S is the magnitude of surface tension. I think yeah, this is for a film. The surface tension is 100 also equal to the surface tension. Okay. Therefore, we have talked about the surface. One week in more than we need to consider fluid surface in contact with other fluids and solids. Okay. So we have just derived that how we equate the work done with the energy and find out what is surface tension. Okay. But surface tension is force per unit length. Just remember that in this case, we have described that extra energy associated with surface. This creation of more surface, keeping other things. So when you are creating more surface, you are adding energy. To appreciate this, consider a horizontal liquid film ending in a bar free to slide uh, over the guides. Okay. Actually, see, area is not 2DL, okay? So here area is nothing, is DL actually, right? Why 2DL?
Okay. Two.
Extra area is D into L only, na?
Uh-huh.
So D into L. If it is D into L, surface
It
tension
would
will
be
become
F by
F by
L.
L. So if you have one surface, okay, but if you have a film,
This is not for soap. This is only for normal.
but no. If you are, so this is a film actually. So it will. That's why two is coming to picture. Why 2DL in this book? They are saying it as 2DL. The surface tension film is the extra area is 2DL. So if it is a film, like both sides there is nothing.
Understood.
If you have only one side, it will be DL only. So if you have a liquid only on one side, then it will be DL only. But in your example in the book, this is just a film. So it will have upper surface, lower surface
So
both.
it is 2.
That's why it is 2DL they are putting. So for a film, it is not F by L, it will be F by 12. In general, it will be F by L. Right? Clear, na?
Yeah, understood.
And also, if this is a water bubble, it will be 2S by R. But it is a soap bubble, it will be 4S by R.
Yeah, that I.
Okay. So these are some of the key takeaways from surface tension. Okay. So okay. Uh, so now we'll try to solve the capillary action. Find out how to find out the capillary rise. Okay. How to find out the capillary rise. Okay. So these things you have understood and remembered, right?
Yes.
See, surface tension, there are no complicated formulas. Okay. These are simple formulas. Okay. That's why if you just remember the formula for capillary rise, if you just remember, okay, what is the excess pressure inside a water bubble? What is the excess pressure inside a soap bubble? Like 2S by R, 4S by R. Surface tension unit, somebody will ask, force per unit length or energy per unit area. Either it can be Newton by meter or it can be Joule by meter square. And from that you can find out, somebody will ask what is the dimension of surface tension and what is surface tension actually. Because on the surface there is an unbalanced force. The inside liquid is trying to pull you. Okay. So when it is trying to pull you inside, the surface will be in a state of tension, right? That's why it is called surface tension. What is surface tension? Tension means what? It is a force. Okay, so the surface is under some influence of some force, inside force. So somebody is trying to pull it inside, so it will be in a state of tension, right? Why tension? Because somebody is trying to pull you. You want to go out, so that's why you will be in tension. Okay, so something is being done against your nature, like that's why you will be under state of tension. Okay. So I have written it as probability because of the last class. So Did probability help you in your mathematics exam? Anything came related to what is that? Binomial?
Mm. Bernoulli's trial and Bayes theorem.
Did anything come? Did it help?
It came in 5 marks, two questions.
Okay, so how to derive the equation for capillary rise? Okay, so let us say I have this container. Okay, so I have this container and I have a capillary tube. Okay, I have a capillary tube, right? So you will find capillary action that water will rise only if the diameter of the tube is less. Lesser is the diameter, higher is the rise. So in general, by a thumb rule, they say any tube of less than 6 mm diameter can be called as capillary tube. Because more than 6 mm diameter, you cannot see the significant capillary rise. Okay, so let us say my water looks like this, a concave surface. Okay, so if it is mercury, it will be a convex surface. So there is a concept of angle of contact and adhesive force and cohesive force that I was telling. Like cohesive force is force between two similar substances. Adhesive force is the force between two dissimilar substances.
Yeah.
Okay, so this is my water, and you can see here it will form a. You can see the
Meniscus.
concave surface. You can see the meniscus more predominantly here. Okay, so this is my. There is water inside, and this is my capillary tube. Okay, so here by how the question normally comes is by how much height the water is going to rise. Okay, so this height you just go to the tilde lower level of the meniscus. This height is h. Okay, this height is h, and let us say the outside it is a, and somewhere inside take another point. This is b. Okay, and yeah, and if we take a enlarged view of this capillary, okay, this capillary, it will, okay, let's take a enlarged view. So this is my capillary. Okay, so this is what it is. So what will happen? So you draw a tangent to this surface. Okay, so the tangent to the surface, and this is also the tangent to the surface, and this angle, the angle between the meniscus and the solid, adjoining solid line is called angle of contact. So this is angle of contact. Angle of contact. This is angle of contact. So this is a acute angle now. Okay. So there can be case where you will have obtuse angle as angle of contact. This is suppose mercury. Okay. Mercury, it will be like this. So you draw a tangent, right? So with the solid, whatever angle it is making, that is called angle of contact. So this is obtuse angle, whereas this is acute angle. So, and let us say okay. So there are two things. One is your radius of meniscus. Let us say this is like this. So my meniscus, my center is here. Okay. So this is my radius of meniscus. Okay. So this is kind of radius of meniscus, capital R. Okay. whereas this one is radius of the tube, small r. And because this is theta, okay, so this is theta, so and this angle is 90 degree,
Yeah.
okay, so this will be 90 minus theta, and this angle is also theta, right?
Yeah.
Because this is perpendicular to this and this is perpendicular to this,
Yeah.
so this is this. So if these two lines are theta, the angle between perpendicular to these two lines also will be theta.
Theta.
So there is a relationship between the meniscus radius and the tube radius. Okay, so r cos theta is equal to small r. Okay. Okay, so that is there. Then how do we derive the equation for capillary rise? Okay, so uh, see, if you consider the pressure here, okay, so this pressure is actually atmospheric pressure acting here. Atmospheric, because it is open to the outside, right? So sorry. Okay. The pressure, the pressure inside the pressure of water inside the tube, just as a meniscus of water is less than the atmospheric pressure. Consider 2 points A and B. This they must be at same pressure. Okay. So what is written here? Pi minus
PO.
PO. O is written. Huh?
Yeah.
Okay. This surface of water. The surface of water in the capillary is concave. This means that there is a pressure difference between the two sides of the top surface. This is given by Pi minus PO. Okay. So let us say this is my top surface. Okay. So there is a pressure between two sides of this. This is given by Pi minus PO. Okay. So what is happening? Let us say what is written here? This is PO, right? This is PO, right?
Inside is PO, outside is
Okay, good. Okay. Why this is called PI then? Okay. Okay. Okay, let us say the pressure here is Pi, that is the inside the concave surface. Okay. Okay.
Yeah, yeah.
This is the inside the concave surface, the pressure is Pi, whereas other side of the concave surface, let us say the pressure is PO,
Yeah.
other side, right?
Liquid pressure.
Liquid side. So there is a pressure difference. Okay. So this Pi minus PO
Delta
is called as delta P is nothing but your 2s by r. That we know. Right? This is Pi minus Po in case of the meniscus. Okay. So, thus the pressure of water inside the tube just at the meniscus is less than the atmospheric pressure. Okay. Pressure of the water inside the tube just at the meniscus is less than, consider 2 points A and B, and they must be at the same pressure. Okay. So let this pressure be inside the PO, right? Let it be PO. Okay. So this is inside, it's out. This is PI, right? Inside this is PO. Okay. So let the pressure inside the is PO. Then pressure at A, like say pressure at A is equal to, let us say pressure at B, because at same height the pressure will remain the same, right? So PA is equal to PB, right? So what is PA? What is PB? PB is equal to PO plus H rho G, because this height is H. Rho is the density. So PB is equal to PO plus H rho G, right? So PI, so which is equal to, so PA is equal to PB is equal to PO plus H rho G, right? This is the equation.
Yeah.
So that is nothing but PO plus H rho G. So which is again equal to Pi. Why? Because here atmosphere is acting, here also atmosphere is there.
Okay.
Both are exposed to atmosphere. So it is atmospheric pressure, right?
Yeah.
So PA is equal to PB is equal to PI. And we have done that Pi minus P0 is equal to whatever. So now from this equation you can find out Pi minus Po is equal to H rho G. Right?
Yes,
So Pi minus Po is equal to H rho G, and
Pi minus PO is
and again
2s by r.
Pi minus Po is equal to 2 into surface tension by R. Okay.
So H is equal to 2s by r.
So
2s by
H rho G is equal to
2s by r.
2s by R.
So H is equal to
So
2s.
H is equal to
2s by rho g r.
2s by rho G R. So this is what the
Capillary
formula for capillary rise. Okay. So yeah. So this is the key here. This pressure is equal to this pressure. Pi is equal to Pa. If you know that, then the most of the concept is clear. Because here also atmospheric air is acting. Here also atmosphere is acting. It is exposed to atmosphere. That's why this pressure is equal to this pressure. But Po, which is inside the liquid, it will be higher than that by this value. Okay, so because of this H rho G formula, you can correlate it. Okay, because you are comparing this pressure with Po pressure. So Pa is equal to Po plus H rho G. But Pa is nothing but equal to Pi. So, and again you know Po minus Pi or Pi minus Po is equal to 2s by R. So combining that surface tension means the
Delta P
differential
formula.
delta P concept you are combining with pressure
Rho G.
H rho G concept. So when you add those things, you will find the capillary rise. Okay. So he has given some example, like say water has surface tension of, let us say water has surface tension of 0.073 Newton meter. Right? He has given surface tension. We will write it as S. Okay. Because sometimes we write it as T also, because it is tension. We write it as surface tension. But so it is given. So for example, suppose in your numerical they will ask, okay, the surface tension is equal to 0.073 meter, and let us say the radius of the tube. Okay, the radius is 0.05 cm. Okay, 0.05 cm. Okay, that means it is 0.5 mm or so. Okay, 0.05 cm means 0.5 mm. Using, you can imagine 0.5 mm means just like a needle, very small. Okay.
It means
Then,
high capillary rise.
high capillary. So this from the table he has got what are the surface tension values. Actually in table 10.3 the surface tension values are given actually. So I will write it down. The surface tension values of water is 0.07. So water surface tension value is 0.07 Newton meter. Okay, this is for water. Okay, mercury is 0.43. So mercury surface tension is 0.43. Okay, Newton per meter. So you can see it is almost five times more or 6 times more. So that's why. Yeah, gases has much lesser surface tension because you can see there is no attraction, they are not under tension, they are almost free. So gases will have like 100 times less, like helium has 100 times lesser surface tension. Oxygen has 0.01, that means it is 7 times lesser surface tension than water. Okay, okay, so in the numerical it is given the radius is equal to 0.05 cm. Okay, and then the surface tension is like 0.073. Okay, so you know rho is nothing but your like water density. So water density you know is 1000 kg per meter cube. Always remember this, right? See, air density is something around 1 kg per meter cube, like 1.029 or something. So always remember this density of water and density of air. Water is almost 1000 times more denser than air. Okay. So you know the water density is 1000 kg per meter cube, and you know what is the G value, which is 9.8 meter per second square. Okay. So this is your density of water. So never ever forget the density of water value. 1000 kg per meter. G is 9.8 meter per second square. So the formula that we have derived for capillary rise is this, right? So we know we need surface tension, we know S, we know R, and this R you have to convert it to meter.
Yeah.
Okay. So you have 0.05 cm, it will become 0.004 0.004, right?
Into
0045 meter, right?
Yeah.
This is that. So by replacing all this, you can find out the capillary rise. Okay. So this is I'll take you through the quick numericals on Venturi meter or the Bernoulli's equation of continuity. We will do some 10-20 numericals related to that. Quickly we do. These are, see, Bernoulli equation of continuity is what? A1 B1 is equal to A2 B2.
Diameter, find diameter or velocity.
That is based on conservation of mass. Okay. So mass can never be destroyed. So whatever is passing through one cross section of a tube, it will pass through the other cross section. Maybe the cross sectional area will change. So if the cross sectional area decreases, the velocity increases. That's the equation of continuity from conservation of mass. Bernoulli's equation is for conservation of energy. Okay. So there are three types of energy: pressure energy, velocity energy, and the datum energy. Okay. So everything you can put in the unit of datum. Okay. So that Bernoulli equation is H plus half rho v square. Okay. Plus P. Right.
Yeah.
This is so. P by rho g, I think. Okay. P by rho g.
Rho G.
Yeah. So P. So everything will have a unit of meter. Everything will have unit of length or whatever. So you have to be very very careful because it has to be unit consistent. Okay. So H plus half rho v square plus P by rho g is equal to constant. That is the governing Bernoulli equation. Whereas A1 V1 is equal to A2 V2 is your equation of continuity. So
It's
best
P by rho and half V square. Not
P
half-
by rho.
Yeah, and half V square, not half rho V square.
Okay.
Say okay, yeah, it will get
If you want to make it a height unit, then
Yeah.
rho v square you have to write.
Yeah.
Okay. So normally you will write it in the height unit.
Yeah.
So that datum head
Understood.
we call it as velocity head. We call it as pressure head. Head means what? Head means unit of height.
Yeah.
That's why we will not write as P. We will write as P by rho g. Why P by rho g? Because we know P is equal to rho g h, right? So H unit will be P by rho g. Okay. Clear?
Understood.
So suppose in a aircraft it is moving. So in the numerical they will be giving on the top surface your velocity is this, in the bottom surface your velocity is this, and height on the top and bottom the height difference will be very negligible. Neglect that height percent. So you know that okay, my velocity energy at the top velocity is this, at the bottom velocity is this. So in the equation you can easily write about the velocities on the both sides. So they will ask what is the pressure difference between the bottom surface and the top surface and bottom surface of the wing. So you will just write P1 minus P2 is equal to half rho V2 square minus V1 square. That's all. So that pressure, if you multiply it by the wing area, they will give the wing area. That is the lift force that is being generated.
Understood.
Okay. So we can do a lot of numerical on equation of continuity and Bernoulli's equation. Okay. But surface tension is a simpler concept, not too much of mathematics there, just the excess pressure 2s by r, 4s by r, and then capillary rise is equal to 2s by rho gr. Just these formulas, if you remember, you can do. Okay, and many physical phenomena can be explained using surface tension. Okay. Okay, thank you. We'll, next session we'll cover. We'll do some 10-20 numericals on equation of continuity and Bernoulli equation and surface tension. Anyway, we have done. You can find out from your CET or JE papers if anything they are related to surface tension.